This video is going to go over a little bit on the Poisson's ratio experiment. The first thing we're going to do is go over a little bit of notes and background for Poisson's ratio in the experiment, and then we're going to actually do the experiment, and then we'll go over a little bit on what you'll see in the data and kind of what to show for your report and the overall process on how to use your data for the analysis section. So just kind of a little bit of overview of what we're doing. The Poisson's ratio experiment is going to be covering a flat bar that's subjected to uniaxial loading. The main thing that we're looking at in this experiment is being able to confirm Poisson's ratio for an aluminum sample. In this case, we're looking at an aluminum sample of 6061 T6 aluminum. So just a little bit of background, kind of covering some notes for the experiment. We're going to measure strain in the axial and transverse directions using strain gauges. So we're going to place we have placed two strain gauges, one in the axial direction and one in the transverse direction, and we're going to measure Poisson's ratio. So general information, axial stress, which we've covered a little bit before, is the stress in the axial direction is force divided by your initial area. So what we're going to do initially is measure the interior region of our sample, both the length and width, and that will be the area segment of our sample. So when we see a positive value, that's going to be usually a tension force that's greater than 0. When we see a negative value, that's a compression value on our strain indicator. And I'll go into that a little bit more when we see it on the P3 strain indicators that we do with the experiment. For transverse strain, it's negative when subjected to an axial load, and the internal segment contracts when it's pulled. So if the bottom segment is acting as a clamp and all our stress or our force is coming from the vertical direction, then we're going to be getting a vertical force applied to our sample. So that narrow region will then contract a little bit as it's being pulled. So Poisson's ratio, which is what we're primarily looking at in this experiment, is the negative ratio of transverse strain to axial strain. So when we find our strain values using our strain gauges, we'll have that value for a transverse strain and our axial strain, and then we'll use those two values in order to calculate our Poisson's ratio answer. So axial strain is the increase or decrease in length resulting from stress acting parallel to the longitudinal axis of the specimen. The axial strain is defined as an extension per unit length. So similar to kind of what we talked about also in our tension test experiment, our axial strain is our change in length divided by our initial length. So strain is our non-dimensional unit and is positive in tension and will be negative in compression, also kind of previously mentioned within these notes. Our Young's modulus value, which will also be one of the values we're calculating in this test, is our stress is equal to our modulus of elasticity times strain. So if we want to find our modulus of elasticity value, then we can divide our stress divided by our strain. So the way we're going to be doing this in this experiment is using strain gauges. So strain gauges are used to sense strain on the surface of a material. So these are attached directly to the surface of the material in a multi-step process. We're not applying the strain gauges in this particular experiment, we're just using them to analyze our data. You will probably have an experiment later, not necessarily in this class, but where we will go over how to actually apply a strain gauge and applying your strain gauges to a particular material. So this figure illustrates a couple different examples of strain gauges. In this case, we're using a linear type strain gauge, so two individual linear strain gauges, but there are multiple different types of strain gauges that can be used depending on what you're wanting to do your analysis of or about. So in general, strain gauges convert force, pressure, etc. into a change in electrical resistance that can be measured. The way that we'll do this conversion in our case is using one of the P3 strain indicator boxes, which I'll show in a minute in the notes and then also illustrate in the actual experimental video. When external forces are applied to our specimen, stress and strain result. So stress is the object's internal resisting forces and strain is the displacement and deformation that occurs from that force. In general, strain gauges can be used to pick up expansion and contraction, and the orientation of the strain gauge and how it's applied is important in this particular case. So the axial strain gauge will pick up a certain value, and the transverse strain gauge will pick up a certain value. In general, the main purpose of the strain gauge is to directly, indirectly determine stress and its variation with time. Strain is sensed in the gauge by using the physical principle that a wire changes resistance when stretched. So as stress is applied to our specimen, then the strain gauge will feel or analyze, that force that's being applied and convert that to a value that we can use to analyze our particular strain. So just some general examples of where you might see some strain gauges in use. A lot of cases lately have been in the medical field, so strain gauges are incorporated into instruments such as syringe pumps or kidney dialysis machines. They're also important in geotechnical tools, so if you're looking at tunnels, buildings, concrete, bridges, they can be fixed on structural load-bearing components to measure the stresses along load paths. They also can be used in CT scan machines and various other applicable sections. So this is just kind of a brief overview of a couple of instances you may see them used. This is in no way a comprehensive list. So in general, the gauge factor for our sample is one of the instruments that we use to put into our P3 strain indicators. Therefore, there's three main things that we look at in inputting the values before we can start our experiment. Those are the gauge factor, the bridge type, and then also the instrumentation for how we input the wires. So in general, for the gauge factor, it's manufacturer based. So they'll be provided based when you purchase your particular strain gauge. So this is kind of just an example of what you might see when you purchase your strain gauges and the information they give you along the lines of your strain gauge. So the strain gauge is applied in this particular region. So the gauge factor in this particular case for this example is 2.01. In this case, this is just for this example, for this image. That's not the particular gauge factor that you will use for the experiment we're doing today. In our case, the gauge factor is 2.11, but this is just to illustrate where you might find that value on a strain gauge purchased from a manufacturer. So this is kind of the boxes that illustrate our P3 strain indicators. You'll see a set of bridge types that are on the top of the machine, which I'll illustrate a little bit more when we see the actual experiment. But these are the exact format for the strain gauge indicators that we use within our labs. And this is kind of just a closer viewpoint of the strain gauge indicator. So they have 4 channels, channel 1, channel 2, channel 3, and channel 4. And those are the locations that the strain gauge wires are plugged into in order to adhere to our strain gauge value. Also on this P3 strain indicators, you'll see a bridge type button, and that's where we'll input the type of bridge for our analysis. In our case, this will be a quarter type of bridge. The K here, that's the gauge factor, will be that 2.11 that's used in our experiment, or if you're looking at the manufacturer picture that we have a little bit further up on the notes, then that would be the 2.01 in that case. You'll also see a balance button here, and we hit that button twice when we before we start our test, and that zeroes out any previous issues or load that may be already applicable inside the strain gauge indicator, or just making sure we zero out the beginning of our experiment. So in terms of the lab experiment procedure, I type this up in the notes that are available. I'll go through this with you as we perform the experiment, but we are looking at doing the experiment to test our Poisson's ratio and how close that is on our 6061 T6 material. In our case, we are going from 0 to 2,500 pounds in 500-pound increments, and then we'll reload or decrease our load from 2,500 pounds to 0 pounds to show our initial state again. So in terms of some example calculations, this is just a little bit before we get to the end of the experiment where I'll show you what you can do with your data, but this is just some initial calculation to show what we're actually looking at. So we're looking at 3 main calculations for the experiment. One is Poisson's ratio, which again is the negative of our transverse strain gauge over our axial strain gauge. So in this example, if our transverse strain gauge is negative 105, then and our axial strain gauge is 318, then our Poisson's ratio value is exactly 0.33. In this case also, I want to mention that the values that you see on the strain gauge indicator are in microstrain, which means that the value you see is actually that value times 10 to the minus 6th. So the value you see, if it's 100, 200, 300, 1,000, all of those values are in microstrain, which are 10 times 10 to the minus 6th, or 10 to the minus 6th. Also in our axial stress value, then we're looking at our stress in the axial direction being force divided by our initial area. The initial area values for our length and width are mentioned in the lab manual. We'll also measure those ourselves for our particular specimen, but in this case, if we're going by the lab manual value, if we look at, say, the 500-pound case divided by the length times the width of our particular specimen, then we're looking at an axial stress value of about 3,900 psi. So the third thing that we'll be calculating through the experiment is our modulus of elasticity. So since our modulus of elasticity value is stress is equal to modulus of elasticity times strain, then our modulus of elasticity is stress divided by strain. Therefore, once we find our stress value at a particular load, then that value is our axial stress term. And then our strain value, which will be our axial strain value because we're looking at the axial force direction, then we have 318 times 10 to the minus 6. So therefore, if we have our stress value, divided by our strain value in the proper unit, then our modulus of elasticity value is 12,380,000 psi in this case, so for this particular load. So this is for the 500-pound case. Or we can look at it as 12,382 ksi. So you can use it in either units that you want to input this in, but you can use psi or ksi, or you can use a different unit if you like. Just keeping it in this unit just makes it fairly easy. So additionally, there's a section in your lab report that uses the accepted values for the material that we're looking at, so I've included these values here. Again, we're using aluminum 6061, so our modulus of elasticity value is 10 million psi or 10,000 ksi. Poisson's ratio is approximately 0.33, and our yield stress is about 40,000 psi. So this is kind of the initial overview of kind of background on our experiment, that what we're going to be conducting today. And next we'll get into actually conducting our experiment. This is our aluminum sample of 6061 T6 aluminum. The first thing we're going to do is measure the length and width of the narrower region of this specimen. So our length is approximately 0.505 inches. I'm just measuring in more than one place just to get a representation. That location was 0.509 inches. Now we're going to look at the narrow region's width. So we're going to start again at 0 inches. And this is about 0.2595 inches in that location. We'll just get one more spot. And this location is about 0.2615 inches. So our specimen has now been placed into the flat grips. The bottom grip has been tightened, the top grip has not. So you'll see it's a 6061 T6 aluminum sample, where the grips have the larger region of the sample, and the interior region is a little bit smaller where the strain gauges are placed. So our P3 strain indicator shows our bridge setup for our P+, S-, and D120 setup for our strain gauge wires. So we're using the quarter bridge setup because we're looking at a sample that's got in purely tension for our experiment. So our P3 strain indicator boxes here, similar to our notes regions earlier in our video, has our bridge type, gauge factor. So if we look at the gauge factor first, we'll see that we're looking at channel 1 in units of microstrain, and the gauge factor has been set to 2.11, which is correct for our handout. Similarly, if we go through the other channels, you'll see that the other channels that are applied will have a similar reading. Additionally, you can change the gauge factor just by scrolling over and increasing or decreasing that value. If we look at the bridge type, you'll see it's a quarter bridge type, and you can cycle through a various number of settings for this also, for like half bridge shear, full bridge shear, and then also a few other variations. So we're going to leave it at a quarter bridge setup because we're looking at that tension environment. Again, this is our 6061 T6 aluminum sample. It's a flat specimen with a larger region at the grip section and a smaller diameter in the region of the testing where the strain gauges are applied. So we're going to open our software, and in this case we can use a tension test experiment because we're looking at applying tension to our specimen. So as you saw in the specimen we just looked at, there are two strain gauges that are applied, one in the axial direction, which is our vertical strain gauge that's about a 90-degree orientation, and then another strain gauge in the transverse direction, which is placed horizontally in about a 0-degree orientation. So while that opens, we'll just take a look at the specimen again. So we're making sure that it's not tightened at the top yet because we haven't zeroed the load within our computer program system. So we can go ahead and balance the P3 strain indicator. So we press balance once and then confirm by pressing balance again. It's going to say it cannot balance the channels that do not have wires plugged in, and then we save the settings to balance our P3 strain indicator. So you'll see if it doesn't necessarily read all zeros at first, that's not necessarily uncommon, but we can rebalance it if we want to try and get at 0. So we'll rebalance it here. You'll see it says that again it can't balance the ones where wires are not plugged in, and we'll see that if we save, we have 0 readings for both channel 2 and channel 4 for both of the sections that our strain gauges are adhered to. So now we'll open our tension test experiment. We can open any tension test that's in the setup or of our various options. So in this case, we'll just look at our new tension test that's our most recent one. So now we'll wait for this program to open. Now that our program's opened, we can look at the orientation. So if we want to be able to use our controller, we notice that it's set to that play pause region I just pointed out. So if we press to unlock the controller, now it shows that we have control over our MTS machine. So now we want to zero out our load. So if we go to our load, we can zero signal to zero out any residual load within our computer system. So now we have 0 load applied there. We have zeroed our strain indicator, and we can now tighten the top grip of our specimen. So if we tighten this grip, we will see that we'll have some residual load applied to our specimen. And we have about 16 pounds of force applied onto our system. So now we'll see for about 16 pounds we get some strain gauge readings. So we can use our fine tuner to measure our load because we don't want to go up or down on our load too quickly. So now we can lower our value to approximately 0 pounds. And you can record our values for 0 pounds of our strain gauge reading. So channel 2 will be our axial gauge, and channel 4 will be our transverse gauge. So now we'll go up to 500 pounds and record our 2 strain gauge readings again. We'll do this at 500, 1,000, 1,500, 2,000, and 2,500 pounds, and then we'll go down to 0 pounds and re-record our strain gauge readings at 0 pounds. Now we're going to go over an example of what you do for your lab report once you obtain your data. So this is just an example set of data on what we'll be calculating for our example set today. So if this will kind of be the layout of what you'll be given on the downloaded section for your particular data, or you can use the set of data that's provided in this video. So now we have our 0 to 2,500 pound load test range, and then the axial and transverse strains that were calculated during a previous experiment. This is not necessarily the values that were conducted in the experiment that we did during this video. So these values is what you actually obtained from your experiment. So now we're looking at what to do with the analysis of the data. So those 3 values that we talked about previously in terms of what we're going to be analyzing today are Poisson's ratio, axial stress, and modulus of elasticity. So if we're looking at Poisson's ratio first, since we know that our transverse strain, the negative of our transverse strain divided by our axial strain is our Poisson's ratio, we can do equal to our transverse strain gauge divided by our axial strain gauge. So just don't forget to include the negative symbol. So then we get a Poisson's ratio value at our 500-pound load case of approximately 0.35. So we can take this little black cross at the bottom corner and drag this down, and that will be the values for our remaining load cases. So that's how we calculate our Poisson's ratio section. If we're next looking at our axial stress, then we're looking at force over area. So in this case, we have the area of our bar. So if the area of our bar, if the length of our bar is 0.512 and the width of our bar is 0.248, then the area of our bar is those two values multiplied together for our rectangular section. Therefore, if we're looking at force divided by area, we can do equal to the load case that we're looking at divided by our area. So we're looking at a first value of 3,937. So if we drag that down again, oh, sorry, my fault. We also have to put the dollar signs in front of our area term for both the letter and the number, because that value is the same area for each of our corresponding load cases. Therefore now we can drag that value down again. So now you see it populates the value for our axial stress at the remaining values. So our third term is our modulus of elasticity. So since this value is the stress divided by strain, then we can do equal to our stress value divided by our axial strain value times 10 to the negative 6th. And then if we want our data in KSI, so say if we leave this here, then our value is in PSI, and stress at each point, we can drag this value down, and that will populate our value for each value. So then we'll be converting this value to 10 million PSI. If we're wanting the value in KSI, then we can just divide this value by 1,000. So that will give our values in KSI. You can leave it in PSI or KSI, either way is fine, but that divided by 1,000 will just convert our value into KSI. So we'll also look at the average value. So this is just an additional, so if we're looking at average for Poisson's ratio, axial stress, and modulus of elasticity. You don't have to put these values here. I don't think each of these is required for for an average value. You can check the table in the lab report handout to make sure which average values are needed. I'm just going to include them here to show you how, but you can include these in the lab handout or in the spreadsheet. Either one is fine. So if we want to know the average of Poisson's ratio, we can do equal to average of our Poisson's ratio values. So our average Poisson's ratio value is 0.34. Our average axial stress is 11,813. And our average modulus of elasticity is about 9,200,000 KS, or sorry, 9,196 KSI. So these would be the average values for our experiment in this example. There is a section down here in the example that discusses strain correction. Pretty much what's being done here is offsetting these initial zero values, averaging these two terms, and adjusting your axial strain and transverse strain to these points. You can either adjust these values, which in turn would be slightly more accurate in terms of your interpretation. But if you want to use these direct values, that is okay too. But our strain correction terms, the way that these are calculated is your first value is adding these two values divided by 2. So our -3 plus a -13 would be -16, which would have our adjusted value of 8. So in this case, with the strain correction, our Poisson's ratio value, is 0.34, which is slightly lower than this 0.35 value we had. So you see it kind of adds up our values a little bit better than even what we had, but that's how the strain correction values are performed. So the last step of what you'll be doing for the analysis, the last step for the analysis of the experiment, not including the question segment or the discussion, is the 2 graphs that we'll be looking at. In this case, we'll be looking at the axial and transverse graph, and in this case, we're looking to make sure that our load values line up according to what we would be interpreting in terms of a fairly linear relationship. So to do this, if we want our axial one, we can copy our axial gauge values and paste them here. And if we want our transverse gauge values, we can copy these and paste them here. So now if we look at the graphical arrangement, we have our axial strain values on our x-axis and the point that each one is at along that trend. So now we see that our linear relationship for our axial gauge is consistent, and then similarly for our transverse strain gauge, we see the value in our negative relationship for our fairly linear relationship here as well. So you would include these 2 graphical values along with the calculation and the 2 questions in the discussion, and that would be the analysis for your experiment for this particular Poisson's ratio lab. I hope this helps in terms of giving you a little bit of information in terms of the analysis and the experiment. And that concludes our experiment on Poisson's ratio.